Howdy. I wanted to complete the problem that we were doing at the end of class today. And in this problem, we have a block of mass M. Problem mass actually asks, how large would the block have to be? And we have a second block, block B, of mass 2 kilograms. I'm just going to write that as 2 kilograms right here. And we're told that mu s here is equal to 0.3, and we're asked how large would M have to be to keep the system from moving. And so of course we began by simply doing free body diagrams for each one. Our free body diagram for M is going to show, of course, weight pulling down, which I'm going to label as mg, or 10 times M, and a normal force pushing up. Because there's a rope attached to M, there's going to be a tension, and because the problem says that there is a frictional force, there is going to be a frictional force. Will it be static or kinetic? Well, we're trying to keep the system from moving, and so therefore we're looking at a static frictional force. And that's the free body diagram for M. Over here on the 2 kilogram block, we have a tension T, and we have a 20 Newton weight pulling straight down. Having done our free body diagram, we can immediately do analysis. Let's do the easy one first, the 2 kilogram block over here. The sum of forces on the 2 kilogram block in the y direction is going to be equal to T minus 20. And we're going to use Newton 1 because we are not moving and therefore not accelerating either. And this immediately tells us that the tension is equal to 20, which I can go and write into the diagram over here as well. And if I now do the sum of forces in the x direction on M, then I get that the tension is pulling to the right, and the static frictional force is pulling to the left, and therefore that has to all add up to 0 because, again, our system is not moving, and that immediately tells us that the static frictional force is equal to 20 newtons as well. And these two forces here and here cancel each other out. And then we do the sum of forces on the mass in the y direction, and that's going to give us normal force pushing up minus 10m, the weight pulling down, and that's equal to 0 because the block is not accelerating off the table. And that immediately gives us that Fn is equal to 10 times the mass m. So we have a number of nice little pieces that we have discovered, and now we just need to put it together in order to figure out the mass m. And the thing that we have not yet taken into account is the value of the frictional force. Since we are at the maximum possible frictional force, in other words, we're just on the verge of moving, we're going to say that F sub s is equal to mu s times the normal force. And now if we plug in all of our values, we have a 20 Newton force for the static frictional force. We have a value of 0.3 for mu s, and our normal force is equal to 10 times m. Solving for m by dividing both sides by 10, and dividing both sides by 0.3, we get m is equal to 6.3 kilograms. 19, nope, it's going to be 6.7 kilograms. There we go. So, that's really kind of it. If I were solving this in the wild, then I would probably do what I was doing at the end of class there. I would immediately assess that my tension had to be 20 in order to keep these two balanced, which means that my friction had to be 20 in order to keep these two balanced. And therefore, the mu, well, I could immediately go to Fs equals USFN, and since I have those values, then I get a quick solution. The same equation that we had at the end of all of this. So the algebra, once you get the algebra under your belt, you get to the point where you can start doing it a little bit in your head. But for now, I think the safest way to go is with sum of forces.